Experiences are what people love the most about travel. That's why they love Viator. They have over 300,000 bookable experiences and something for everyone. Plus, their travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. Download the Viator app now and use code Viator10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
With Kroger brand products from Baker's, you can make all your favorite things this holiday season. Because Kroger brand's proven quality products come at exceptionally low prices. And with a money-back quality guarantee, every dish is sure to be a favorite.
These are a few of my favorite things.
Whether you shop delivery, pickup, or in-store, Kroger brand has all your favorite things. Baker's, fresh for everyone.
Today's show is brought to you by ExpressVPN. Protect your online activity today and find out how you can get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Visit tryexpressvpn.com/space to learn more.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello yet again. Thank you for joining us on the Space Nuts podcast. My name's Andrew Dunkley, your host, and with me as always is Professor Fred Watson, astronomer at large. Hello, Fred.
Hey, Andrew. How are you going?
Oh, I'm very well. How are you?
Yes, I'm surviving nicely, thank you.
That's good to hear. Good to hear.
Yes.
Seems like only minutes since you told me that. But anyway, let's talk about this week's episode, episode 159 of the Space Nuts podcast. We're going to look at a situation that I find quite surprising. But, you know, having worked in radio for 35 years or whatever it is, and radio is very common, radio waves are very common in the universe, but now it's been discovered that there might be a ridge of plasma emitting radio waves connecting two galaxy clusters, which just sounds mind-boggling. When you consider that the limit of a radio signal in space is 50 light years or something. So this is rather fascinating. We will also knock off a couple of questions in what is yet another shortened version of our podcast. We're going to look at a question about dark matter pushback from Dr. Robert Scott. Thank you, Robert. And Kevin Rutherford's asked us about the Michelson-Morley experiment. Could be the Michelson-Morley experiment, depending on how you pronounce his name. But it looks like Kevin's detected there could be a contradiction in that experiment, and well, we'll investigate that. Might take a little bit of work to figure that one out. But first, Fred, let's look at these radio waves that seem to be sort of working between these two galaxy clusters. Sounds rather fascinating.
It does indeed, and it's something that's been suspected for decades, actually, that we would find something like this. And it probably means we will eventually find a lot more of these. So what's happened is that two clusters of galaxies, and of course galaxies are these huge aggregations of stars and gas and dust, one of which we live in, called the Milky Way galaxy. But we know that galaxies come in clusters. Two of them, which have been studied in detail, have shown an interesting thing between them. These two galaxy clusters are they're not close together. They are relatively close together on the sky, but when you look at the scale that you're talking about, this is millions of light years apart that they are. It's maybe a little bit unexpected that you'd find bridge of material between them. But clearly people have been expecting this because astrophysicists have been looking for it. So the two galaxies rejoice in the name of Abell 0399 and Abell 0401. And you might notice those numbers are only 2 apart, which tells you that these two clusters are next to one another. Galaxy clusters, by the way, are usually they usually have the name Abell in front of them because they were catalogued by an astronomer called George Abell, who did a lot of his work in the 1980s. I actually knew him. He spent some time in Edinburgh at the Royal Observatory where I was working because he wanted to use some of the photographic material that we had to identify his galaxy clusters. He was a delightful man. He's no longer with us, but it's nice to see his name cropping up every time you talk about galaxy clusters. So Abell 399 and Abell 401 are these two galaxies which may well be about to merge together. In other words, undergoing a collision. But what has been observed is a bridge of material between them. And it's plasma, as you said. It's basically energized atoms. And the interesting thing about it, and I think this is why this has become such a big story, is that to have a plasma like that, you need magnetic fields to excite it. And so the ridge tells you that there is magnetism connecting these two galaxy clusters. And that's a magnetic field over a very, very large distance. Yes. So if you think about a bar magnet, the kind of thing you might put in your pocket, this is something like that, but it's 10 million light years long.
Wow.
And it's the plasma. So it feeds into trying to understand how magnetic fields originate. And in fact, that's what a lot of modern astrophysics is about. Where do magnetic fields come from? It's one of the reasons why Australia is involved with the Square Kilometre Array project, the largest telescope in the world, which will be completed within the next decade in 2 places, one in Western Australia and the other in South Africa. SKA is the next big thing in radio astronomy, and they will certainly be using that facility to look for bridging magnetic fields between clusters of galaxies, because among its stated intentions, the stated aims of the SKA is understanding the origin of magnetism in the universe. Now, it wasn't the SKA that was used for these observations, but it was a sort of what you might call a distant cousin of the SKA, a thing called LOFAR. LOFAR is the low frequency array. So it's a set of radio telescopes looking at low frequencies from the universe. It's still the VHF band as far as we're concerned in terrestrial communications, but that's low frequency for astronomy. LOFAR is actually located in Europe. In fact, in several sites in Europe. I visited one of them some years ago, which I think was at Nancy in northern France. And it looks like just an array of poles stuck in the ground. It's not elegant dishes or anything like that. LOFAR only needs relatively simple antennas, but there are many of them, as indeed the SKA will be. The SKA will have 136,000 antennas shaped like small Christmas trees, or actually shaped like large Christmas trees, made out of bent coat hangers. That's what it looks like. But it's very high-tech stuff.
Just like one of my old cars, by the sound of it.
Yeah, that's right. It's probably got bits of old car in it as well. I can tell you, actually, that when they made the prototype of that, they used to act as a base for each of these antennas, and there were several thousand antennas in the prototype model, the Pathfinder. They actually used concrete slabs with holes in the middle, which they bought second-hand from the post office in the United Kingdom, because they were telephone manhole surrounds. You have a manhole cover where you at the bottom of the hole you've got all these telephone cables with a metal cover on it. Well, they've got a concrete surrounding, and somehow the Square Kilometre Array people found a cheap deal to buy a couple of thousand of these manhole
That's
cover.
Hilarious.
Yeah, and that's what. So that was the base of their prototype array. They had to change the design because they realised that for 136,000 of these things, it was going to get very expensive in second-hand manholes. So they thought of another way. But anyway, so that will be what the low-frequency Square Kilometre Array component in Australia will look like. But LOFAR has, the one in Europe has essentially made this great breakthrough that we've found magnetic fields between clusters of galaxies. I'm sure the story will move on as the square kilometre array evolves. We might find that there's a web of magnetic fields connecting all galaxy clusters. That could be one of the discoveries that might be made, and that would directly play into trying to understand where magnetic fields come from.
Yeah, well, so it opens up a question in my mind, because as I understand it, Abell 0399 and Abell 0401 are merging. Yeah. And our galaxy is going to merge with the Andromeda galaxy. So one wonders if we'll start sort of exchanging these materials.
It could be already happening, Andrew, because that will be something that probably from our vantage point will be very difficult to detect. I do have friends in the business, though, who are specialists on cosmic magnetism, and I might ask them about it, because that's a really good point, that maybe our galaxy and Andromeda, which are closing on at a speed of, I think it's around 200 kilometers per second. That closing speed means that they're on a collision course. There may already be a bridge of material between them that links them in the way that we see these two galaxy clusters linked. Really interesting comment. Yeah. Well done, Andrew.
Oh, thank you.
Be writing astronomy papers.
They'd be very short. Yeah. And I don't think they'd qualify. But, I only... so at 200 kilometres per second merging rate, and how long before the merger happens?
It's about 3.5 billion years.
It really does let you know how big the space is between us.
That's right. Yes, that's right.
It's extraordinary.
Yeah.
All right. You're listening to Space Nuts. Andrew Dunkley here with Professor Fred Watson. Now, let's take a little break and find out more about our sponsor, ExpressVPN, rated number 1 by Tech Radar. This is the one I use. I've been using it for a couple of years, and I love it. When I joined ExpressVPN, they were brand new to the market, but I read a lot of reviews and did a lot of comparisons. And there was just something about their business model that I particularly liked. And a couple of years down the track, honestly, can't complain. Their interface is very easy to use. Their service is second to none. I've had to contact them a couple of times about certain things that I wanted to do, and they were brilliant. So you may be wondering why I do need a VPN at all. It's all about privacy. Do you really want big tech companies, governments and others knowing what's going on with your online activity? Even if you're having nothing to hide, it just feels downright creepy. I think you'll agree. And governments are getting more and more interested in what you're doing every day. And so, protecting your privacy is what VPN is all about. And how often do you run across websites that you want to get information from only to find that they're geo-blocked? This is becoming an increasing problem, but ExpressVPN solves that problem for you. Now, if you go to our special URL, you'll see quite a list of things this service can help you with, things you may never have thought of before. As I say, it's the one I use, secure, fast, and it just works. So protect yourself online today and find out more about how to get 3 months free at tryexpressvpn.com/space. That's tryexpressvpn.com/space for 3 months free with a 1-year package. Try expressvpn.com/space to learn more, and you'll find the link details in the show notes and on our website. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Now, Fred, before we get on to today's questions, something's popped up in the news which is rather extraordinary. We've talked about space tourism and the organisations, private organisations that are looking at putting people into space, suborbital flight, that kind of thing. People get to experience for $200,000 a pop or whatever it is. 0G for a short period of time and then glide back to Earth or get rocketed back to Earth or whatever. It depends on who they go with, I suppose. But now NASA's playing the game.
Yeah, they are. That's right. And I guess you can put it in context. The context is that the current US government administration sees the private sector essentially taking over the space station within the next decade or so. It may even be before that, might be within the next 5 years, that NASA wants to open the station to private industry, and that they will eventually, private industry will take over the running of the space station for whatever purposes might be deemed necessary. And one of those purposes could well be tourism. So this is a sort of opening gambit in the private sector for NASA to start opening up the possibility of space tourists now, to ease the transition from the private sector to the from the publicly owned sector to the commercial sector. So we've got the deal that you can now buy a holiday on the International Space Station, as you've been able to do before. And you and I spoke about this. Well, no, actually, the space station itself. So for about a decade, during the early 2000s, a company called Space Adventures brokered a deal between Roscosmos, the Russian space agency, and a few really wealthy people who wanted to go into space. Because in those days, as is now actually, in those days, while the shuttle was still flying, US astronauts were ferried up and down to the space station with the shuttle, but cosmonauts went with the Soyuz spacecraft, which was a 3-seater spacecraft, but only 2 were used. So Space Adventures did this deal where a passenger could fill the 3rd seat.
That's right.
I think there were 7 takers for this. The least that was paid, we know, was $20 million for a few days on the space station, and it was probably more than double that for the most expensive one. The prices that are being quoted now, though, are a bit higher than that, because the ticket to get there could be as much as $58 million US, and this would come from one of the organizations that are going to be ferrying stuff up, most notably SpaceX, which is interesting. I would have thought the price would have come down because SpaceX, of course, reuse their boosters, and that means that their price per kilogram to get into orbit should be cheaper. Anyway, that's the price that's being paid, and there is a daily rate for the space station of $35,000 US per night. That probably includes a cup of tea in the morning as well. You kind of hope so.
Yes, yes, but you wouldn't be able to drink it like you normally would.
No, that's not. Yeah, seed spreads all over the place.
You have to take it out of a plastic container or something.
With a straw.
With a straw, yeah. So, all right, that'll be interesting. I'm sure there'll be takers. I would love to be able to afford it. I think it'd be marvellous. But you know what? Never going to happen. Now, let's move on to some questions. And this one comes from Dr. Rob Scott, who resides on the Sunshine Coast in Queensland. And no derogatory remarks this time about the state of origin because it bit me in the face big time. Now, he says, if gravity can interact with the fabric of space-time, gravitational waves, could dark matter just be a pushback from this fabric on matter? Could this account for the high rotational speeds, some steadying force from the fabric of space allowing higher speeds of matter without galaxies breaking apart?
It's a nice idea from Rob, and I think his thinking is good. So I suppose what you could do is you could say, okay, we're faced with this problem. Galaxies rotate faster than they should be able to stay together. You see a galaxy, you can measure its rotation, you can look at it and see how much mass you think is there. But it turns out that if that's all there is, then the thing should have flown apart. So there are 2 possible ways of dealing with that question. One is what is now the accepted standard version, that there is this material called dark matter, which envelops the galaxy, and it's the gravity of dark matter that holds the galaxy together. But there is another possible interpretation, which was suggested very early in our understanding of dark matter, which is back in the 1980s. Mordechai Milgrom at, I think it's Tel Aviv University in Israel, suggested that it could be that we've got our understanding of the way dynamical forces work. And he proposed something called MOND, which is modified Newtonian dynamics. Now, in a sense, that aligns with what Rob is suggesting, that you've got what he calls a pushback from the fabric of space, that would manifest itself as a force field, which could be interpreted as a modification of Newtonian dynamics. So it's got connections with what was proposed back in the 1980s. The bottom line is that it doesn't work because whilst you can use MOND, or a sort of pushback force, to interpret galaxies holding themselves together when they shouldn't, it doesn't work when you look at clusters of galaxies, and it doesn't work when you look at the evolution of the universe as a whole. And that's the problem, that the idea of some sort of material, dark matter, is fully consistent with everything else we measure in the universe, whereas modified Newtonian dynamics isn't. And that's why it's largely been abandoned. Although I have to say, and he might well be listening to this podcast because I know he's a listener, one of my colleagues is about to embark on a PhD looking at MOND, modified Newtonian dynamics. So maybe Rob Scott on the Sunshine Coast, Dr. Rob Scott, will be happy to know that people are investigating still this idea that it's our understanding of physics that's wrong, not the fact that there is some material that we don't see. I think it's good thinking, and you never know. We will wait to see the end of Peter's PhD thesis in a few years' time and find out whether MOND might actually be the answer.
Could be. Thank you, Rob, for your question. Really appreciate it. Now we turn our attention to a question from Kevin Rutherford. Kevin lives in Macclesfield in the UK, and it looks like he's a kindred spirit of yours, Fred. He said, I studied the Michelson-Morley experiment at school, and indeed in first-year physics at St Andrews University in 1977, shortly after Fred's time there. Yeah, about 70 years before Fred was there. After Fred was there. Anyway, briefly, does the LIGO experiment contradict the Michelson-Morley theory? Both experiments used interferometry to detect properties of whatever it is that Earth is moving through, and yet one concluded there is no ether, while the other concluded that space-time can wobble. Is there a contradiction, or was the Michelson-Morley experiment not sensitive enough for its purpose?
It's a great question. And it's not a fellow St Andrews graduate there. Good to hear from you, Kevin. And there's another connection with astronomy there, of course, Andrew, because Kevin's from Macclesfield in the UK. It's in the north of England, so it's pronounced Macclesfield with a very short, flat A. Aye, Macclesfield. It's where the Jodrell Bank Radio Telescope is, very close to Macclesfield. So that pioneering radio telescope, the UK equivalent of our Parkes dish here in Australia, is very close to Macclesfield. In fact, you pass it on the M6 if anybody's passing that way. But don't look while you're driving, because you can easily run into something else rather than the telescope. So it's quite a long way away. Great question. So, okay, what is the Michelson-Morley experiment? It's an experiment using light waves. And the idea was, this was performed many, many times in the 1880s, from the 1880s onwards, because people believed at that time that there would be something called the ether. And the ether was supposed to be the component of the universe which transmitted light. So, and the analog, of course, is that on the Earth's surface, we hear sound waves because sound is transmitted by the atmosphere. And so physicists of the day figured that you needed something to transmit light waves and suggested that there would be an ether. That was what it was called. It was the raw material of space, if you like, that transmits light waves to it. So experiments were done, as I said, starting in the 1880s to try and measure this ether. And the way they were done was to use this thing called an interferometer. Actually, it's usually called a Michelson interferometer because he's the guy who invented it, to show that light would have different properties in one direction as distinct from another. And why did they choose two particular directions? Well, one of them is the way the Earth is moving through space. And we know the Earth is going at 30 kilometers per second around the sun. And we also know that the sun is being carried at 250 kilometers per second around the center of our galaxy. So that the Earth has a motion through space. And so the argument was that this interferometer should be able to detect that. Now, if the ether existed, that would be a very, very gross effect. The Michelson-Morley interferometer would show it up, as though it was being illuminated by a searchlight. It would be very, very obvious in that experiment that there is an ether. And so that's why we recognized after the Michelson-Morley experiment that there isn't an ether, and it's what led then to special relativity, because we now know that the speed of light is the same no matter what direction you're going through or you're seeing or moving through space. That's what the Michelson-Morley experiment did, the Michelson-Morley experiment. Now, LIGO, the Large Interferometric Gravitational Observatory that you and I have spoken of many times,
Yep.
is just a Michelson interferometer. It's the same instrument. But so if there was an ether, that interferometer will be absolutely overwhelmed by the signal from that, the fact that the Earth is moving through space. But what we're detecting now is just vibrations in space itself, which are at a much, much more subtle level. So the last line of Kevin's question was the Michelson-Morley experiment not sensitive enough for its purpose? The answer to that is no. Had there been an ether, it would have picked it up.
Yeah.
Because it's a gross effect. But it was not sensitive enough by a very long way to detect gravitational waves. They need the kind of exquisite sensitivity that we've spoken about with the LIGO interferometer, which can detect changes in length that amount to 1/10,000th of the diameter of a proton. It's still just staggering stuff.
It is.
The original Michelson-Morley experiment was nowhere near that kind of sensitivity. So there are no contradictions. But it's a really interesting question and a good thing to think about as well. It gets me getting my mind back to second year or first year physics at St Andrews. Back in the day, you were wrong actually about it being there 70 years before Kevin was. I should tell you that the University of St Andrews was founded in 1413, and I was there very shortly after.
Yeah, fair enough. Kevin also writes that he found FW initials in his desk, but he's not sure what they meant. Anyway, thank you, Kevin, for your question. Really appreciate it, and hopefully you got a bit more of an insight into what you were pondering about, which is terrific. And thank you as always, Fred. It's been a great pleasure as always.
Thank you to you too, Andrew, and we'll speak again soon, I'm sure.
We will. Fred Watson, astronomer at large. And just a reminder, patreon.com/spacenuts. You can certainly subscribe to the Space Nuts podcast there. If you're an Instagram user, you can find our parent organisation, Bytes, BITESZHQ, on Instagram. You can also find us on Facebook. Just do a search for Space Nuts, and YouTube as well. Until next time, thank you as always for your contribution to this little podcast and for listening in, and we'll catch you in the next episode of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor. This has been another quality podcast production from Bytes.com.
With Kroger brand products from Baker's, you can make all your favorite things this holiday season. Because Kroger brand's proven quality products come at exceptionally low prices. And with a money-back quality guarantee, every dish is sure to be a favorite.
These are a few of my favorite things.
Whether you shop delivery, pickup, or in-store, Kroger brand has all your favorite things. Baker's, fresh for everyone. With Kroger brand products from Baker's, you can make all your favorite things this holiday season. Because Kroger brand's proven quality products come at exceptionally low prices. And with a money-back quality guarantee, every dish is sure to be a favorite.
These are a few of my favorite things.
Whether you shop delivery, pickup, or in-store, Kroger brand has all your favorite things. Baker's, fresh for everyone.